Hello and welcome to the lecture on Chapter 13, Waves and Their Properties. Waves are one of those things that doesn't seem as immediately physical and as immediately useful for physics and industry as, say, heat engine does. But they are also indispensable to any discussion of physics because it turns out not only to have a ton of applications and a ton of theoretical work, not only because of whatchamacallit, sorry, not only because of their immediate applicability in music or sound or uh, the waves that you see in the ocean, but also because it turns out that light and matter also are made of waves and can be described in the same way that waves can be described. So, what is a wave? So, a wave is fundamentally a pattern. So, a pattern propagates out from the place where it was created, uh, which is, but the pattern uh, is what moves out, not the material that it's moving through. So mechanical waves are something that require a medium to travel through, but the medium does not travel, just the pattern of the wave. So for example, if you drop a pebble into the water, the um, mechanical that would be a mechanical wave because the pebble causes a disruption that travels along the water, but the water is not pushed from side to side. It's just pushed up and down as the wave travels by. The wave itself is the information of the disruption, which does travel from the initial point where you drop the pebble out in ripples through the entire pond that you're looking at. And then this is true of waves such as in water or waves in strings that you will see in instruments. But it is not true of light, which is not a mechanical wave, as it does not need a medium to travel through. So you cannot hear somebody speaking to you through space. So even if in space, rather, so even if you yell as loud as possible on a spacewalk, nobody's going to be able to hear you because there's no air through which the sound wave can travel. But you can still see each other because light travels through space because it doesn't need the medium to travel through. So there are two types of waves that the book defines. A pulse wave is a sudden disturbance in which only one wave or a few waves are generated, such as in the example of the pebble. Thunder and explosions also create pulse waves. A periodic wave repeats the same oscillation for several cycles, such as in the case of the wave pool, and is associated with simple harmonic motion. So what that is associated with simple harmonic motion means is that the up and down motion of the wave is going to it's going to look like a sine wave, where a sine wave is the shape of the water that you see in this picture right now, where it goes up and down and up and down and up and down. So the pul so a periodic wave is going to repeat that same oscillation for several cycles. Uh, and it's going to be the same type of motion that you see, or the same, it's going to be describing the same type of motion that you would see for simple harmonic motion, which is what you see when like a pendulum is ticking back and forth, or a spring is going from side to side. That is also going to follow a sine wave. So another definition that we can come up with is a longitudinal and a transverse wave. So a longitudinal wave is one where the wave causes the medium, or causes whatever is whatever is being held by the wave, whatever pattern the wave is manifesting itself. So for example, here you could have a slinky like you see when you're doing jump rope, that's going up and down, and that's going to be a transverse wave, as it goes literally up and down, and up and down and up and down. So that is a transverse wave, and that's going to be the type of wave that you see in, say, a wave pool, or a guitar string, or a piano string, or actually it turns out that the electric field caused by light travels through space as a transverse wave. Longitudinal is the other type of wave, where instead of being transverse, which means that it's perpendicular to the direction of travel. So you see that in this picture, actually, I didn't notice this, but you see these arrows pointing in the direction of travel from left to right, and then you see that the wave is shaking up and down. That means that it's perpendicular to the direction of travel, which means that transverse wave is perpendicular, which is another word for transverse. While longitudinal wave, you shake it in the same direction as the direction of travel, and the wave travels, the disturbance of the wave travels along in the same direction. So this is like sound, where you vibrate the air and it causes there to be pockets of high pressure and low pressure that go out in the same direction that the sound is traveling in. So another way you can see this is if you hold a slinky and just hold it like this, you'll see that it's going to create areas of high density of coils and areas of low density of coils, and that's going to be the wave that you're seeing traveling along in a longitudinal wave. So we're not going to get into the mathematics of this. We're just going to talk about some of the properties of waves, which are similar to the properties of simple harmonic motion. We have amplitude, which is the distance between the resting position and the maximum displacement of the wave. So the amplitude of this wave that you see on the right would be the distance from the dashed line to a crest, which is the highest point, or to a trough, which is the lowest point. So the x in this case would be the amplitude of the wave. The frequency is the number of waves passing by in a specific point, passing by a specific point per second. So if you're on the ocean and you get hit with a wave 20 times every minute, then that would mean that you have a frequency of 20 times per minute, which would be a frequency of 1/3 of a wave hitting you every second. And then the period is the time it takes for one wave cycle to complete, so it's kind of the opposite. So if you get hit 20 times per second, then that means that the period would be every 3 seconds. And then wavelength is the distance between the crest of one wave cycle. So if you look on this diagram right here, it's a snapshot in time rather than a snapshot in space. So it's a snapshot in time, which means that time is frozen still for this moment, and you'll see that the wavelength is the distance between these two crests, these two high points, between each other. Just the wavelength is the distance between the crest in one cycle, while the period is the time, the distance between the time between each crest hitting you in a specific point. And then the wave velocity is how fast the wave is traveling, which is just as the wave moves by, it travels, as you see the duck or the seagull there, as the wave goes by, it's going to hit the duck, raise it up, and then bring it back down, and then raise it up. So the wave, as the wave goes from side to side, it is traveling at some velocity, which is called the wave velocity. And then the wave velocity is something that's relatively constant through a medium and is related to frequency and wavelength. So it's actually equal to frequency times wavelength, but I don't want to get too bogged down in the mathematics. So what's important is that as frequency goes up, wavelength goes down. So if you have a high frequency and small wavelength, if you have something going through the same material, so sound going through air, for example, at the same temperature and the same material is going to be going at a constant speed through the medium. So if you have a higher frequency sound coming out of a speaker, then it's going to have a smaller wavelength than if you have a lower frequency sound coming from the same speaker going through the same air. So we're just talking about the different types of materials, and then none of it's immediately obvious why we would care, but it starts to get useful when we talk about constructive and destructive interference, which is what happens when you have a superposition of two different waves, where a superposition is you take one A wave and add it to another. So in this case, if these two waves, which have the same wavelength and the same frequency, or the same frequency, are next to each other, then, and they're something called in phase, which means that the high points line up with the high points and the low points line up with the low points, then that means that when you put the two waves together, the resultant wave is going to be twice as high as the either of the two waves, which is called constructive interference. And then destructive interference is when they are completely out of phase with each other, which means that the high points are at the low point of one wave are at the low points of the other wave, and vice versa. So if that's the case, you'll see if you add these two waves together, the resultant wave is just going to be a zero flat line with no wave whatsoever, which is called destructive interference. So most waves are not going to be the same frequency or the same wavelength. So if you have, if you have superposition of two different waves with different wavelengths, then the resultant wave is going to look more complicated and have a combination of constructive and destructive interference, as you'll see here. So the one of the last things that I want to do, or actually, I want to just go on for a second about why superposition is useful. One of the reasons is why it's useful is that this is actually how by studying this and by studying a more complicated version of this, this is how we came to the ideal that light was constantly traveling in any direction through a medium. So what we did, or what physicists did, what Michelson and Morley did when they were proving this in the late 19th century, was they took a laser beam of light, or not a laser beam, but yeah, they didn't have those back then, but they took a beam of light with the same wavelength and shot it along two different paths. And what they saw was a pattern of constructive and destructive interference as the wavelength traveled along the two different paths and was either in phase or out of phase at different was either in phase or out of phase at different points. But when they rotated the experiment so that it was going through, the light would be going perpendicular to the direction of the Earth rather than along the direction of the Earth. This is a very, very oversimplified version of it, but when they rotated the experiment so that instead of moving in the same direction of the Earth, one of the light beams was instead moving perpendicular to the direction of the Earth. Instead of direction of the movement of the Earth, instead of seeing what they expected to see, which was a different interference pattern, different constructive and destructive interference, what they actually saw was the same interference pattern, which means that the light was moving in the same velocity and moving along the same pattern, no matter if you were going in the same direction as the velocity of the Earth, or if you were going in a different direction than the velocity of the Earth. So that was the basis for special relativity and all that chapter, which I didn't get into at the time because we didn't have this idea of waves and we didn't have this idea of superposition, but it is very useful, and I just wanted to get into that before going on so we can get an idea of why we want this to be the case, why we care about waves in the first place. So standing waves are something that you'll also see. So a wave does not seem to move and appears to just stand in place vibrating. Such waves are called standing waves and are formed by the superposition of two or more waves moving in opposite direction. The waves go by, move through each other with disturbances adding as they go by. So wave one, so what happens is that you have a wave moving along, say, a guitar string or a piano string, I would bring out a guitar right now to demonstrate it, but it's kind of hard to see without a strobe light, and I don't have a strobe light. But you have one wave that goes one direction, and then it's still vibrating. It's not a pulse wave, it's a continuous wave that continues to vibrate and move along the guitar string. And then you have that wave reflect back and start going in the opposite direction, while the initial wave that's the initial vibration that was causing the string to vibrate or to send a wave in the initial direction is continuing to send waves. So as these two waves meet, the initial wave and the reflected wave, they go through periods where they either constructively or destructively interfere with each other. And the result is what you see on this bottom left-hand graphic, where it either builds up constructive interference or builds up destructive interference. So it builds up each other, then nothing, then it builds up in the opposite direction, then nothing, then it builds up in the same direction, then nothing. So this is called a standing wave. And there are various conditions that must be met in order for this to be allowed. And one of them tends to be that one of them tends to be that in order for this to have constructive and destructive interference, is that if each end is tied down, then the wavelength of the wave that passes through has to be such that each end is going to be at one of these what we call nodes. So if you look at the resultant case again on the bottom left-hand corner, you'll see that there are points where the wave doesn't go up or down. It's always going to be at a 0 point. So those are called nodes. And two of those nodes for a guitar string have to be at either end of the guitar string, because those ends of the guitar string are hammered down. They're completely held in place. And the wavelength has to be such that the number that each continuous wave has a number of nodes where each side is held together and each side is at a node. So, for example, for these types of instruments, the guitar or the piano, you have to have it so that half of a wavelength is equal to so half of some multiple of a half wavelength is equal to the length of the guitar string. So that's why only certain sounds come out of a guitar when you plug it with different L or at different lengths, because it's these certain wavelengths that are allowed. And these certain wavelengths that are allowed only allowed because they have the nodes at either end. So it has to be some multiple of half the wavelength is equal to the length of the guitar string. So you see here we have 3 nodes, which is allowed. We could have 2 nodes, which would be allowed. We could or we can have 4 nodes, which would be allowed, or 5 nodes, but it has to only be such a wavelength that there are that number of nodes over the course of the length of the guitar string. And then this is also different for different instruments, but so for example, for a flute, one of the edges has to be a node because it's vibrating and it's closed off at that edge, while the other edge has to be an antinode, which is what we call these areas that go up and down and up and down at the highest point. And then in that case, you would have a different formalism or a different formula for the number of wavelengths that are allowed in a certain length of flute. So that is all that I have to say. If you have any questions, as always, feel free to reach out to me. And I look forward to seeing you again soon.